In the event that you need to study tonight, the tangent and cotangent, you'll have that ability. All right, so the tangent function. The tangent function, again, it's just going around the unit circle, and it's dividing the sine and the cosine. It's dividing the y and the x, right? But we've decided that there are some convenient points to do that with, and two of the convenient points or positions to do that yield something very useful for us are at pi over 2 and negative pi over 2. And actually, let's do this. If I'm going around the unit circle, okay, the reason I say pi over 2 because that is the point 0, 1, right? And when I divide y by x to get my tangent, I get 1 divided by 0, which is undefined, right? So it generates this asymptote here. If I were to continue around the unit circle in the same direction, the next place that I have similar division is right there, correct? And that angle is what? 3 pi over 2. So that's going to produce that asymptote right there, correct? Now, usually we do not consider those our parent function asymptotes, okay? What we traditionally do is we work from here that way to get to that same point. Well, what would that green measurement be? Negative pi over 2, okay? So that is a way to determine where that other asymptote needs to go at negative pi over 2. Or if you were to just go around the unit circle counterclockwise and you find that this is the distance between two asymptotes, then can't I start at pi over 2 and apply the same distance this direction and get my asymptote there? Okay, so I'm going to have another asymptote at x equals negative pi over 2. And those are the two asymptotes that we use to graph the first period of our tangent function. Because we like to be around the y-axis. We like to be around the origin. Does that make sense? So then, another point that is very useful for us is this point here where my cursor is, which is 1, 0, right? And if I divide 1, 0, I get 0. If I'm plotting radians against y divided by x, or sine divided by cosine, I get that point right there. So 0, 0 is a really nice point for us. And that's what's going to happen every time we do a tangent function. Halfway in between your asymptotes, you are always going to cross your x-axis, or your axis of wave. Okay, if you've moved up or down, it maybe not be the x-axis, be the axis of wave. But that's what we do. Now, halfway in between this point A and that asymptote right there on the unit circle would be that point right there where my cursor is. What is that angle halfway in between in the first quadrant? Pi over 4, right? And the x and y values are radical 2 over 2, radical 2 over 2, right? When you divide those, what do you get? 1, okay? So what happens is that halfway, and the reason why we do this is because of the unit circle, but halfway in between that interval right there, you're going to plot a point at a height of 1. So we have pi over 4, 1. Okay? Now, if I was working from 0 to negative pi over 2, well, that would be going this direction on that green curve, right, in the unit circle. Halfway in between there would be negative pi over 4. You might think it's analogous to 7 pi over 4, which it is. It's coterminal, okay? But because we're working, we want to be on the left-hand side of the y-axis here at negative pi over 4. That's why we're going to go that clockwise direction. Or the x and y values for that point on the unit circle the same numbers. One of them is positive, one of them is negative, though, right? We'll take the same numbers, one being positive, one being negative. I get a negative what back? Negative 1. Okay, so negative pi over 4, comma, negative 1 should be that point right there. And if you think about it, that is the exact same point if I would have gone 7 pi over 4, comma, negative 1, except for that point, obviously, is going to be over here with the 7 pi over 4 radian measurement. Does that make sense? Okay. So now a smooth curve through those 3 points should generate 1 period of that function. Okay. So tomorrow on the quiz, I've got it all set up with the x-axis and y-axis and all that kind of stuff for you. It looks very similar to that. And I'm just going to ask you, can you produce those pieces of information? Okay. Now, on that quiz, I'm going to need, I'll make sure that I tell you this when I give it to you, I'm going to need your asymptotes to be defined. I need you to draw them. I need you to accurately put points for those 3 points. Okay. In the past, I would get people to do something like this, where we have our asymptotes, but then they just go, oh man, I'm not sure. Okay, and do something like that. Okay, or they know the behavior, and they know it should go through 0, 0, and they do something like this. That's terrible. What's going on with this thing? They do something like that, and something like that. Okay, or maybe more like that. And what happens is if they do that haphazardly, they're not going through those points of pi over 4 comma 1 and negative pi over 4 comma negative 1, right? Okay, they might hit pi. It looks like I kind of hit pi over 4 comma 1 there, but you're not telling me exactly that you know you should be going through that point. Okay, I need those to be determined, declared on your picture. So that's the tangent function. Now, if I'm interested in doing the cotangent, there's a couple things you can do here. Okay, and I don't care how you view it. There's 2 ways. You can go around the unit circle the same way we do with the tangent, and then divide. Now it'd be x's divided by y's to create some ordered pairs, and hopefully you choose convenient values of pi, or sorry, of your radians to do that. So probably 0, pi over 4, 3 pi over 4, and pi would be good ones to choose. Or you can know that once you have the tangent, the cotangent is a transformation of that. You can slide everything to the right, pi over 2 units. Think about tangent and cotangent, right? Tangent and cotangent. We talked about this, and we'll talk about it in more detail later. But whenever these functions are the same word, but one of them has that prefix co on it, it means that they are transformations of one another 90 degrees, right? Okay. Meaning then, to get the cotangent, I can take the tangent and shift it 90 degrees. Okay, and it really doesn't matter which way. We usually go to the right. But I'm going to shift it 90 degrees to the right, or pi over 2 radians to the right. Does that make sense? Now, that will not generate 100% the cotangent, because we also have to take the tangent, shift it to the right 90 degrees. We need to reflect it across the x-axis. Okay? So this is what I'm going to do. I'm going to take, if I've got my tangent, I know I'm going to move this one here, this asymptote, pi over 2 units to the right. So it should go out to pi. I'm going to move this one, pi over 2 units to the right, so it's going to go to 0. Does that make sense? I'm going to take each one of these points. B is going to go pi over 2 units to the right. A is going to go pi over 2 units to the right. C is going to go pi over 2 units to the right. Is that all right? Now I say we need to reflect across the x-axis. Goes up, comes down, and now if I type in the cotangent of x from 0 to pi, that is the curve then that we need. Is that all right? Okay. So that's one way of quickly developing the cotangent if you know the tangent. And hopefully tomorrow in front of you, I have you do the tangent first, and then right next to it is the cotangent. So hopefully you do the tangent correctly, and if you do that, then by all means, I think you should be able to get the cotangent right. But that's not the only way you can do it. Like I said, we can use the unit circle approach. So I'm looking at the unit circle here. Obviously, this is my first ordered pair that I'm interested in. It's 0 radians, and the point is 1, 0, and cotangent, remember, is x divided by y. If I take my x value divided by my y value, 1 divided by 0 gives me what? Undefined. So x equals 0, we have that asymptote. Okay? The next place that I would have something like that, think about going out, so people come up here and they say, okay, well, I have 0 or 1. If I divide x divided by y, 0 divided by 1, that's okay, right? So that's not an issue, but when I get here, it's essentially the same point as that one, right? Except for a negative. With the division, negative 1 divided by 0 is still undefined, right? So x equals positive pi will be my next asymptote. And that's the reason that really shows up there. Is that all right? Okay. We talked just a minute ago, and this is, I think it's important for us to structure our minds this way and our understanding of this way. The transformation process that we went through is kind of secondary to this. This is the actual reason. This unit circle is the actual reason why these asymptotes are there. Does that make sense? The transformations just allow us to see a relationship between a tangent and cotangent that just happens to be true. Okay? But this unit circle approach is the purpose of why we've got these asymptotes. Okay, so that's great. So I'm only interested then in plotting some points here that are in the first and second quadrant. The first point that I think is important for us to graph would be pi over 2, because it splits those asymptotes in half, right? At pi over 2, my x value is 0, my y value is 1. If I divide those in that order, I get 0. So at pi over 2, comma 0, we get a point. Okay? Now, right there where my cursor is, what is that angle right there where my cursor is halfway in between the first quadrant? Pi over 4, right? The x value is radical 2 over 2. The y value is radical 2 over 2, right? Divide those, what do you get? You get 1, okay? So that's why we have the point pi over 4, comma 1, okay? And now over here, do you have the exact same coordinates? Except for x is what? X is negative. So you got negative divided by positive. They're the same numbers. So at 3 pi over 4, we get a result of negative 1. And now that should prove to us that the cotangent does go through those 3 points B, A, and C. Is that all right? I think that's the most logical way, obviously, of doing the cotangent. The reason why the cotangent exists the way it does. If you're a person that prefers to say, I'm going to memorize where my asymptotes go, I'm going to cut the asymptotes in half with the point, A. And now we'll go left asymptote to A. We'll cut that interval in half and go up to 1. And then we'll cut my interval from A to my second asymptote in half. And we'll go down to a point of negative 1 or a higher than negative 1 and get C. That works, okay? But my goal for you guys is to understand why we can kind of use that technique. All right, it's because of the unit circle. We feel like we could ace that tomorrow? Yeah. All right, so tomorrow, just give you the structure of the quiz right now. Tomorrow, first question, graph the sine. Second question, graph the cosine. Third question, graph the cosecant. What's the cosecant? The reciprocal of? Sine, okay? In the past, the people that do poorly on this quiz don't remember that relationship. And they graph the reciprocal of cosine on the cosecant, okay? And that's obviously wrong. The next question is to graph the secant, okay? Then I give you a tangent and the cotangent. And I've already got the graphs laid out for you. Got the x-axis, y-axis labeled for you. Should be pretty quick to be able to graph those 6 things, okay? And then I've got one last question at the end where I've got a function written out. And I just ask you, what are the components of that function? What's the amplitude? What's the phase shift? What's all that kind of stuff? And then you do not have to graph that one. I'm just asking you for the input, okay? The necessary information that you would obtain prior to graphing. Okay, so that's the plan tomorrow. I'm going to go. So it's 18, 19, 20, 21, 22, 23 points. Okay, 3 points for each graph, and those are all or none. So if you mess them, you get 4 of the 5 points right. I'm still going to give you 0 out of 3 on that question. Okay, I think we've been doing these long enough that those things should be be able to be created without any errors in them. Okay. And from your unit circle quiz, guys, I think you guys are taking this stuff seriously, which is good, and I think you'll do fine on that quiz. I don't think we'll have any issues on that. I want to talk today a little bit about inverse functions. You guys remember, obviously, from college algebra that x squared and the square root of x are inverse to one another, right? But they're not I guess the complete x squared doesn't have an inverse. Look at x squared up there. To be an inverse, what did it have? Or to be a function, what did it have to pass? The vertical line test, which means that every x value is paired with only one y value, right? So function-wise, it's the idea of a function being a machine, right? A machine is supposed to do one task and one task only, and I should get the same output every single time, right? It's like taking a food processor and putting an apple in it, and I get applesauce back, right? Put another apple in it, I get applesauce back, right? I put that thing away, I put it in my cupboard. 3 weeks later, I get it back out. I put an apple in it. What should I get out of it? Applesauce, okay? That's one function, okay? I don't put an apple in it 3 weeks later and I get orange juice out, right? That would be a problem with that machine, and that would not be a function. Does that make sense? Okay? So every time I look at x squared, when I put in a 2, I better get 4 back every single time. And 3 weeks later, when I get x squared out of the cupboard and I put 2 in it, I better get 4 back, right? Same thing happens in regards to the inverses. I want the inverses to do the same type of thing. No matter what I put in, I always get an output that is the same, right? Well, in order for that to happen, this function needs to be what we say one-to-one. It has to pass the vertical line test, but it then also needs to pass the horizontal line test, right? Which passing the horizontal line test says that every y value is paired with only one x value, right? Well, look at your graph up there. Envision the line y. Oh, let's make it a little easier. Let's go. Envision the line y equals 4. Are there 2 different x values that go with that line y equals 4? Yeah, they're -2 and +2, right? That's an issue because when I input into the inverse function, when I put input 4 into the inverse function, I want everybody to give me back 2. I don't want half to give me back 2, the other half to give me back -2, right? We need to all be on the same page because I don't want to get that machine out and put an apple in it and not know if I'm going to get applesauce or orange juice, right? I want to know I'm getting applesauce back, and that's the idea about an inverse. I need to know what I'm getting back. So if you remember from college algebra, our task to do this, to say that this thing has an inverse, because if the object is, before I restrict this, isn't an inverse the reflection across that line, y equals x? So if I this curve and reflect it across the line y equals x, okay? Let's see if I can change that color. Okay, I get that red curve, right? Here's the issue. The function that you are finding the inverse of must produce an inverse that is also a function. Because it's the idea that I need to know that my function, my inverse function, is going to take an input and always give me back the same output for that input, right? Is that orange one going to do that? If I put a 3 in there, is that orange one going to always give me back the same output? No, it might give me, 1.7 back, but it might give me negative 1.7 back. I don't know. So we have to be able to fix that. We have to make sure that when we're dealing with functions, the inverse is also a function. So in order to do that, if you remember, we took and we started to truncate the domain, shorten the domain. And as I shorten that domain, you start to see that it's still failing the horizontal line test, right? But over here, this one's starting to pass the the vertical line test at some points, right? Well, I want to restrict this domain of the original function so that everywhere on this inverse, the vertical line test is passed. Does that make sense? So we thought that we had to restrict that domain to there, right? Okay. And if I look at what your domain is for x squared. We were saying that x squared for x value is greater than 0, that is going to have an inverse that is referred to as the square root of x, right? Okay. So if I were to graph, so this curve here is the square root of x, but it's being written as a parametric curve, which is essentially just a third variable, usually time. So if I just write square root of x, you see that that is indeed the inverse, right? Okay, so let's parallel that with, if we understand that concept from college algebra, let's look at the sine function. And I want to go negative 2 pi minus a half, 2 pi plus a half. Let's go y minimum negative 3 to positive 3. Let's see here. Let's get our x-axis to be in terms of pi. There we go. If I take the sine function, okay, does the sine pass the vertical line test? So it's a function, right? Does the sine function pass the horizontal line test? No. So this thing's not one-to-one, meaning that if remember, one-to-one meant that every y value is paired with only one x value. So if I say, hey guys, what's the x value that goes with y being 1? Are some of you going to say pi over 2? Are some of you going to say negative 3 pi over 2? Are some of you going to say 5